Welcome to week 5, everyone. As we promised you when we were going through all those examples with the limit definition of the derivative, we're now reaching the point where we're going to learn a bunch of derivative rule shortcuts so that we will no longer have to do everything from scratch using the limit definition. We're going to come up with 3 basic ones, first of all, that just work on certain generic functions. So this first one, this constant rule, is probably one that I hope you would already guess what the answer is, but we're going to actually prove it here. So suppose that we have a constant function, f of x equals some number k. K could be 1, k could be 17 million, but if f of x is a constant, that means the graph of f of x is a horizontal line. So I think you already should know that the slope of that line should be what? Should be 0. So we're expecting that the derivative of this should be 0. Let's see if we can actually prove it using the limit definition. So I've got my function f of x. I can always go back to my trusty limit definition, f of x plus h minus f of x all over h. Now, the interesting thing about this function is f of x equals k doesn't care what you plug into it. F of 7, f of 23, f of bananas, f of monkeys, they all give k as the answer. So f of x plus k is just k. And f of x is just k. So now I just have 0 over h. So the limit as h goes to 0 of 0 over h. And remember, we're not thinking about h actually equaling 0. H is just getting near 0. So if you have 0 over even a tiny, tiny number, 0 over 0.0000001, you're still going to get 0, which is what we expected. So our conclusion then, our first not very exciting rule, but d dx of a constant will be 0. So I'm going to start putting these big rules in boxes. This is our first rule, the constant rule. The derivative of any constant is 0. And I hope you agree that that makes sense geometrically since it's the slope of a horizontal line. Let's go to the next one. This is a rule that I have discovered that people will use even if we never tell them that it's a rule. They are just so intuitively think that this is the correct rule, they use it. If I have a function which is 2 functions added together, f of x plus g of x, and suppose I already know the derivatives of f and g, so I already know f prime and g prime, what do you think s prime should be? For example, if in a forest you have living some deer and some moose, and the f represents the number of moose, and g represents the number of deer, and you know how fast the moose are growing, you know how fast the deer are growing in populations, how fast should their combined population be growing? What would you do to the 2 individual rates? You can take a guess based on your own intuition, and now let's see if we can prove it. So again, we go back to our trusty limit definition, s of x plus h minus s of x all over h. Notice that s of x has 2 different x's in it. So when I plug in x plus h, it's going to have to go in 2 different places. So it's going to have to be f of x plus h plus g of x plus h. That's what s of x plus h is, minus s of x, which is f of x plus g of x. And that's all over h. But in here, we can recognize some things that we see. We've got an f of x plus h minus f of x. That's going to give us something familiar. We've got a g of x plus h minus g of x. That's going to give us something familiar. So we can break this up into 2 separate limits. And we're playing, I shouldn't say we're playing a little fast and loose, but we're not exactly justifying all of the things that we're doing with limits. The details on that are all in the graduate credit section of the class, and you are all invited to look at that, whether you are graduate credit or not. But it is legal that if we can break up a limit this way, supposing that these 2 separate limits do exist. But now what do we see? This looks familiar. This is exactly our limit definition of the derivative for f of x. So this is f prime of x. And this is exactly the same thing, except that instead of an f, it's a g. So this is the limit definition for g prime of x. So not surprisingly, if you have 2 functions added together, the derivative of their combined function is the combination of the 2 derivatives. A more formal way of saying that is that the derivative of a sum is the sum of the derivatives. So we can put this together as our sum rule. The derivative of f of x plus g of x is f prime of x plus g prime of x. And so this is useful. If you already know the derivative of x squared and you know the derivative of x cubed, now you know the derivative of the new function whose name is x squared plus x cubed. And just again, remember, d over dx is the operator that says take the derivative of whatever comes next. All right. The next of our three big generic rules is called the constant multiple rule. Suppose that we have some constant, k could be 3 or negative 2 or 17 pi, and we make up a new function, g of x, k, times some function whose derivative we already know. And we want to try to figure out what the derivative of g of x is. So you might be able to guess what that is based on what you know from week 1 about the k, multiplying by a k. What does that do to the graph? Think back to that. But we also have an applet that we've written to help you try to discover what this should be on your own. So that's what we're going to do right now. Take some time to play with that applet, see if you can come up with a conclusion for what you think the rule should be for the derivative of k f of x, and then we'll come back and we'll see if your conjecture is right.